Dr. Butler, and I am going to overview AP Chemistry Unit 6, which is Thermodynamics. All right, so these are the main topics that we would find in thermodynamics. First of all, just what is endothermic and exothermic, have an understanding of that. An understanding of heat transfer and thermal equilibrium, calculations of heat capacity and doing calorimetry, doing a phase changes and calculating phase changes, understanding enthalpy of reactions, and using enthalpy of formations to be able to determine the enthalpy of a reaction, and then for multi-step reactions, use Hess's law to be able to calculate enthalpy changes. All right, so first of all, endothermic and exothermic. Hopefully we have this now. We are going to be using enthalpy terms. So endothermic is positive enthalpy changes, and exothermic is negative enthalpy changes. So it's referring to energy. Is the energy going into the system? That's positive. Or is it going out of the system? That's negative. So endothermic and exothermic processes. Temperature changes indicate these. So if it cools, it's typically an endothermic process. If it heats, it's an exothermic, because when it's cooling, it's the energy from the surroundings is going into the substance, and so you get a cooling. In the exothermic process, it's going out, and so it's producing heat, and it's heating. So the cooling and heating processes, which is often a little bit confusing, and you need to think about that. So endothermic and exothermic processes, there's three main categories. You can heat and cool something. That's straightforward. Phase changes, so going from solid, liquid to gases, are endothermic and exothermic processes. And then chemical bonds, forming and chemical bonds breaking, cause endothermic and exothermic processes. So an exothermic process is one where energy is lost through heating or cooling, phase changes, or chemical bonds changing, and the surroundings gain energy. The heat, this is because of heat transfer. So in this case, heat would have been transferred from the system to the surroundings, or work. The system does work on the surroundings. So we have these two topics, system and surrounding. System is what the chemicals you're studying, and the surrounding is what's immediately around them. It's actually the whole universe, but usually you're looking at what's that. So endothermic is the opposite. The energy is gained by the system because it's lost by the surroundings. Heat is transferred from the surroundings to the system, and work is done by the surroundings, or work is done by the surroundings. Solutions, aqueous solutions can be either exothermic or endothermic, depending upon IMF interactions between the water molecules, between the ions that are trying to get dissolved, between the ion and the water molecules. Overall, it could be endothermic or exothermic. All right, energy diagrams. These are ways of representing a process. So let's say that we are at our reactants, our chemical A's, and we are going to be going up to chemical B's, and we represent that by a diagram like this. This is a positive enthalpy change, and which means that, that we increased our energy. It went from the chemicals had some energy to another energy. So this is endothermic. In the process to do this, it probably needed to get heat, suck out heat from the surroundings, and thus cooling. And so that is that. Going down would be a exothermic process. You may also see this in kinetics. We talked about this. You may see it in a diagram that looks like this to show the whole process, where you have your reactants and the products, and you have an activation energy that you have to overcome. So it is the process of getting up to this transition state. That is an endothermic process. Exothermic process is going down. Where do the reactants and the products lie? that is your overall enthalpy change. In this case, it's negative. The enthalpy change is negative. So energy diagram. Heat transfer and thermal equilibrium. This is pretty straightforward stuff. So you got warmer bodies have higher energy, average. Colder bodies, on average, have colder energy in terms of their kinetic energy. They're moving around energy. Then collisions happen if you have two bodies. If you have a body A and a body B and they're in contact with each other, there's collisions that are going on, and in those collisions there's a transfer of energy. The transfer of energy is always going to be from the greater to the lesser kinetic energy, and that transfer through collisions is called heat. Eventually, thermal equilibrium reaches when the average energy of A and the average energy of B are the same, and there's still collisions happening, but there is no net change of energy from one side to another. And then we have heat capacity and calorimetry. This is where we're starting to get into the math of this, and so it does get a little bit tricky. So we have, in the math, we calculate our heat using heat capacity. There's specific heat capacity and there's heat capacity. Little c in this diagram down here is our specific heat. Big C is the heat capacity of what we are trying to transfer in there. This is a, little c is a number given to a substance like, say, aluminum or iron or water. Water's little c is 4.18. Big C is the combination of the mass of the system and its specific heat. And so sometimes you'll be given heat capacity, sometimes you'll be given specific heat. And you need to be able to calculate this. Q always represents the energy. In our cases in AP Chemistry, we are going to treat heat and energy as the same thing. And because the enthalpy change and the heat are essentially the same thing. The heat capacity equation is this one, and this is the specific heat capacity one, and this other one is the heat capacity. So you need to look at the units of the things that are given to you in a problem to be able to calculate that. So energy is conserved in a process. So when we talk about calorimetry, we may be talking about a bowl, a cup of water. This cup has a certain heat capacity, a C or an MC. And if we put something in there, we could be putting a chemical in there. We could be putting a hot object in there or something like that. But put something in there, and there's going to be heat transfer. Maybe the heat goes from the chemical or the object to the water, and the amount of heat lost by the water is going to equal, so maybe it goes out. The amount of heat lost by the object is going to be the amount of heat gained by the water. That's what energy conservation, that's what it means to be conserved. The transfer of heat energy is not going to be the same temperature change. So the object's going to cool down. That's going to be a triangle T. The water is going to heat up. That's going to be a triangle T. That's not necessarily the same. It depends on the M and the C of the substances. Heating a system increases the energy while cooling will decrease it. And so you'll have a positive Q. You'll have a negative Q. In the end, both of those will be the same. One's going to get heated. One's going to get cooled. And you get that. And so you should be able to heat that. And then also molar heat capacity. You should be able to use molar heat capacity. So your C, if it's in terms of grams, then you're going to use regular heat capacity. If it's in terms of moles, then you need to convert your grams into moles and use that. So look carefully at the units to determine what is going to be used. All right, so calorimetry is a big one, and it's a little complicated with the math. Endothermic and exothermic processes. So temperature changes indicate energy changes. We already know that. So if it cools, that's endothermic. If it heats, it's exothermic. So you need, these are the three processes: heating, cooling, phase changes, and chemical bonds changing. Exothermal process. Oh, I think I already did this, didn't I? That's an extra slide. Sorry about that. Phase changes, specifically about phase changes. Energy can be transferred to cause a phase change. So phase changes are going from solid to liquid to gas or some other combination. You should know all the phase changes and what they do, whether they're exothermic or endothermic. For example, going from a solid to a liquid, you should know the name of it and you should know what that means. So solid is going from a solid to a liquid, that's melting. In order to have that happen, you have to input energy, and so it is endothermic. So you should understand the transfer of heat in these processes. The temperature remains constant in a phase change. So as something is going through here, and here's a diagram of a phase change. In this section right here, we're going from a solid to a liquid. It is the temperatures remaining, that as we add heat, the temperature remains the same. So you have to use now these other equations, heat of fusion and heat of vaporization. If you're going to go from a solid to a liquid, you're going to be using the heat of fusion, which is a number, times the mass of the substance, or the moles of the substance. So you got to look carefully at the units to be able to calculate those things. And then the temperature changes by MC triangle T when it is fully in one phase, but when it's trying to change from one phase to another, you have a constant temperature. The exception to that is supercooling. So if you go down, if I'm cooling a liquid here and I keep on going down, I can actually, if I do it slowly enough, I can supercool it. And that's where it should not go below the freezing temperature, but it may. And then once it starts freezing, it'll increase in temperature and do that. So that concept of supercooling. All right, enthalpy of reaction. You should be able to calculate the heat of a system by a chemical reaction. Enthalpy, and we're going to still give it this triangle H. If it's positive, that is endothermic. If it's negative, it's exothermic. But you are going to generally represent this per mole in a reaction. What is the enthalpy change per mole? And then you can put that into a chemical equation. So you should be able to calculate that in terms of grams or in terms of moles. Could you do this triangle H per gram? You should be able to do that as well. So be able to identify the enthalpy in a chemical equation. So if you have a chemical equation where you have A turns into B, and then you can either represent it by adding an enthalpy term in there, and it may be just an energy term or it may be a triangle H. If it's in the products, that means it's endothermic. If it's in the reactants, it's exothermic. Or it could just say that it has the triangle H. It could give you a number for what that triangle H, and it tells you what it is. Okay, so you need to be able to use enthalpy of reaction and be able to identify that in chemical equations. All right, breaking bonds is endothermic. So bond enthalpy is this next concept. Forming bonds is exothermic, so have those in your mind. Be able to calculate the enthalpy of a reaction by analyzing the bond enthalpies of the reaction. So here's an example. If you have this chemical reaction where we have C2H4 plus HBr turns into C2H5Br, and it's given what the enthalpy of every bond is, you can calculate the total enthalpy by looking at the final enthalpy of all the bonds minus the initial enthalpy of all the bonds and calculate those. So if I look at this, I realize that there is going to have to be one of the double bond is going to have to break, and a single bond is going to have to form between those things. So I have 2 minus 614, and I'm going to add 348 because I'm forming the bond. So I'm breaking bonds, releases the energy, forming bonds, forms the energy. Looks like I have to break this HBr right here as well, and I'm going to form a CBr. So we're going to break the HBr, which is going to be negative, and we're going to form the CBr, which is going to be positive with that. And then finally, there's one extra H here that's going to connect with the C. That H has got to go over and connect. And so we need to form one of these CHs. And so you can figure out using this something in that equation. So that is bond enthalpy. All right, and then enthalpy of formation, you should be able to calculate the enthalpy of a reaction, unit enthalpy of formations of these. So this is an example of that. So we have reaction 1, we have reaction 2, and it tells you the enthalpy of formation of the different substances. It's given by this triangle H with a little F on there, and that's at standard temperature and pressure. And you can see what all those enthalpies are. If it is the pure substance, so like say it's in its natural form, if it was H2 gas, that's just a pure element, and it's in its standard state, its enthalpy equals 0. So you got to remember that. You may not see that in these things. So to figure out the enthalpy of formation, you have to calculate the enthalpies of the products and then minus. So these are the positives, and then minus the enthalpy of the reactants to calculate the overall enthalpy of this. So you could say, what is the overall enthalpy of these two combinations of reactants? All right, and then finally, Hess's law. So Hess's law is representing a chemical equation by a sequence of steps. Each step has an enthalpy. The total enthalpy of the reaction is equal to the enthalpy of the steps. And then you just, if you reverse something, the enthalpy is going to be negative. So here's an example of Hess's law enthalpy. We have something that takes 4 steps, and each step has an enthalpy of reaction. Or actually, these are 4 different reactions, and each one has an enthalpy of reaction. And then we have this overall reaction. And we got to say, okay, how can we get from these reactions up here to the overall reaction? Well, I need 2 M's, and I see that reaction 1 has 2 N's, so I need reaction 1 in the forward direction. I also need 3 Cl2s, and I see that there is a Cl2 over here. There doesn't look like there's any other Cl2s, so I need 3 of reaction 3, right? I need 3 of reaction 3. And then MCl3, hopefully all of those would be formed. I may not need the other ones here. Actually, it looks like I am forming a solid in the end, and I am going to get aqueous up here, and so I need a negative reaction 4 to be able to do this. Well, all of the reactions do this. If I add all of these enthalpies up in the correct way, I do reaction 1, 3 of reaction 3, minus 4 reaction. I probably have to use reaction 2 in some way. I can get my overall enthalpy of the reaction. So that's an example. I'm not going to work through it, but that is Hess's law. All right, and that's it. Unit 6.